Okay, welcome students to this new lecture of soil fertility and plant nutrition. So this is our lecture number 8, and the subject of this lecture is soil acidity. Okay, so in this lecture we will cover the following concepts. What is soil acidity? Sources of acidity, causes of acidity, types of acidity in soils. Okay, now what is soil acidity? Well, soil acidity refers to soils that are acid, that are acid in a reaction throughout the root zone. And this means precisely soils that have a pH that is less than 6.6, and practically this means that soil that have a pH that is less than 7. Okay, so soil acidity is common in all regions where precipitation, that is rainfall, is high enough to leach appreciable amounts of exchangeable bases from the surface layers of soils. Okay, in these soils the concentration of hydrogen ions, in other words, in acid soils the concentration of hydrogen ions exceeds or is more than the concentration of the hydroxyl ions. Okay, these soils may contain large amounts of soluble aluminum, iron, and manganese. Soluble means that the concentration of aluminum, iron, and manganese that is in the soil solution. Okay, now let us look at the sources of soil acidity. What are the sources of soil acidity? The first one is soil organic matter. The second one are clays and oxide minerals. The third one is aluminum and iron polymers. The fourth one are soluble salts, and the fifth one is carbon dioxide. Now let us look at them one by one. Okay, let's start with soil organic matter. Soil organic matter, or humus, contain, humus is highly decomposed organic matter. Okay, the organic matter that has been decomposed by soil microorganisms in such a way now it resists further decomposition. Okay, soil organic matter or humus contains reactive carboxylic and phenolic acid that behaves as weak acids, and these carboxylic and phenolic groups releases hydrogen ions. Okay, this is the chemical reaction when soil organic matter or humus will react, in the presence of water to produce hydrogen ion. We know that, in our previous lectures that the hydrogen ion, causes acidity, and this soil organic matter will react to produce this, or will react to produce this hydrogen ion plus energy and plus inorganic compounds. Okay. The second, is clay and oxide minerals. Now, this one, the dissociation of hydrogen from broken edges of clay minerals and aluminum and iron oxide surfaces contribute to pH buffering in soils, and soils with high amounts of clay and organic matter have high buffering capacity. And in our previous lectures, we talked about this buffering. Okay, And we said that buffering defines the resistance to a change in pH. Okay. Now the third one are aluminium and ion polymers. Now the aluminium and ions displaced from the cation exchange capacity are hydrolyzed, liberating the hydrogen ion. This liberating means releasing the hydrogen ion, and this hydrogen ion will lower the soil's pH. Okay. And these two chemical reactions explain this what is being said by this point. In other words, this aluminium ion will react with water to produce, aluminium oxide plus, a hydrogen ion. This hydrogen ion comes from this water molecule. Okay. This is a similar reaction, but now water reacts in this reaction. Water reacts with ion, to form iron oxide plus, hydrogen ion. Okay. The fourth one is soluble salts. Acidic, basic, or neutral salts in the soil solution originate from 1. Mineral weathering, and 2. Fertilizers and manure addition, especially ammonium sources that produce hydrogen ions during nitrification. Now, for mineral weathering, okay, parent materials, that are rich in granite are acidic, okay, whereas parent materials that are rich in limestone are basic. For this second point, fertilizers and manure addition, especially ammonium sources that produce hydrogen ion during nitrification. This is an example of a chemical reaction. This ammonium will react with oxygen, and this reaction is facilitated by by bacteria. Okay, and the product will be nitrates plus 2 hydrogen ions plus water. Okay, now dynamic equilibria exist between nutrients in the soil solution and on the exchange side. We talked a lot in class about this, about this equilibrium, okay, between the soil colloids and the soil solution. The last one is carbon dioxide. Okay, now decomposition of organic residues and root respiration increases carbon dioxide in soil M, which combine with water to produce hydrogen ions, lowering the soil pH. In other words, when organic matter decomposes in soils, that process will release carbon dioxide, and if the plant roots, when plant roots respire, they will release carbon dioxide. Unlike humans, unlike plants, what they do, they release oxygen by through their leaves, and they release carbon dioxide through their roots. Okay, now that carbon dioxide that has been released by the decomposition of organic matter and by the plant roots will combine with water, with soil water, to produce this carboxylic acid. H2CO3 is carboxylic acid, okay, which is a weak acid. Now this carboxylic acid, because it is a weak acid, it will, one hydrogen ion will dissociate in this in soil solution, in this carboxylic acid, to form one hydrogen ion plus this carboxylic ion. Now, what are the causes of soil acidity? Well, the first one is leaching of bases. All bases, we talked about bases, calcium, magnesium, you know. The second one is cultivation of soils and removal of crop and residues. The third one is nitrogen fertilizers. The fourth one is decomposition of organic matter, and the last one is the acid rain. Okay, let us look at them one by one. Let us start with leaching. Leaching is the major cause of acidity in humid areas where precipitation or rainfall that is high enough to leach appreciable amounts of exchangeable bases. And these exchangeable bases, we say they are calcium, magnesium, potassium, and sodium. Okay. This process encourages the development of acidity in an indirect way by removing those metabolic cations that might compete with hydrogen and aluminum ions on the exchange complex. Okay. The effect of leaching varies with soil type, as you all know. For example, sandy soils which are easily leached and soils derived from parent materials low in bases become acid more easily than soils derived from parent materials rich in bases. For example, dolerite and basalt. Okay. Now the second one is cultivation of soils and removal of crops and residues. This leads to the removal of bases as nutrients from the soil, and it therefore has the same effect as leaching in encouraging soil acidification. Now the third one is nitrogen fertilizers. Heavy application of nitrogen fertilizers such as ammonium sulfate also leads to acidification of soils. Okay. This occurs when the ammonium ions become nitrified as follows. Ammonium will react with oxygen, and this reaction is facilitated by bacteria, from the genus Nitrosomonas, and this ammonium will react with oxygen to produce two hydrogen ions and nitrate and water, a water molecule. Okay, this nitrification process, is essentially an oxidation process, is mediated by bacteria belonging to the genus Nitrosomonas, as I have just told you. Okay, and decomposition of organic matter results in the formation of organic and inorganic acids. Okay, carbonic acid, which is H2CO3, results from the reaction of carbon dioxide and water and has long-term effects of removal of large quantities of bases by solution and leaching. The chemical dissolution of calcite is an example. Okay, so calcium carbonate, in soil fertility we call it calcite, this calcium carbonate, but in chemistry they call it calcium carbonate. So in soils we call it calcite. Will react with carboxylic acid in soil solution to produce calcium plus two molecules of carboxylic acid. Now The fourth one is acid rain. This results from the reaction of water vapor in the atmosphere with oxides of nitrogen and sulfur, coming mostly from the combustion of coal, gasoline, and other fossil fuels. Okay, the results this results the resulting rainwater commonly has a pH that ranges from 4 to 4.5. Okay, and this is the chemical reaction. This 2NO3 plus O2 will react to form two molecules of NO2, and this two NO2 or nitrogen dioxide will react with water H2O to produce this 2HNO3 plus HNO3. Okay, again, in other reaction, not this one. This one is complete, right? In this one sulfur, or this ASO2, or two molecules of sulfate will produce will react with two molecules of what oxygen, sorry, to produce sulfide. This is sulfide, SO3, two molecules of it, and this you know two molecules of sulfide will react with water to produce sulfuric acid, which is H2SO4. Okay, so the last one is acid rain. Soils are generally sufficiently buffered to accommodate acid with little or no increase in soil acidity on an annual basis. However, continued input of acid rain would be, in the long run, have significant effects on soil pH, especially those that are weakly buffered and those that are already quite acid. Okay. Now let us look at types of acidity in soils. We said it that there are three types of acidity, but in this lecture, we will just mention two. Okay, because we talked about these types of acidity a lot. But this is just a reminder. Okay, there are I'm saying that there are we talked about the three types of acidity, but in this lecture we'll talk about these two, and we will try to compare the active acidity versus the exchange or potential acidity. Okay. Now, we said that active acidity refers to the hydrogen ion concentration in the soil solution, okay? And exchange acidity refers to those hydrogen and aluminum ions that are adsorbed on the soil colloids, okay? So, I tried here to grow a soil colloid, a soil colloid for a micelle. This If you assume now this, a rectangle represent, a soil particle or a clay particle, right? And we said that in class that the clay particle has these negative charges. So if we assume now these dashes are negative charges, in this clay, a micelle is a smallest unit of clay. Okay, please understand that. Now, what will happen if we assume area this area is the soil, so represent a soil solution. Okay, so the hydrogen ion that are in the soil solution will be attracted to this negative, to these negative sides of the clay colloids. All right, so one hydrogen ion will be attracted to one negative site in this clay colloid. Another hydrogen ion will be attracted to one negative side in this clay, in this micelle. Okay, Now these negative charges in this area are 3. They are 1, 2, 3. So aluminium ion can be attracted to this area because aluminium ion carries 3 charges. So this aluminium ion will neutralize this negative charge that is in this in this micer. Okay, so now these ions, this hydrogen cation and these aluminium ions are absorbed in this clay micer. So this type of acidity, we call it the exchange acidity or the exchangeable acidity. Okay, and the acidity that is here, that is in this soil solution, we call it active acidity, and is made up of the hydrogen ions and aluminium ions. I hope this makes sense. So the adsorbed hydrogen and aluminium ions move into the soil solution when its acidity is reduced, and consequently the exchange acidity is sometimes referred to as reserve acidity. Okay, the two types of acidity therefore exist in an equilibrium relationship. The amount of active acidity determines the pH of the soil solution at any given time. The quantity of hydrogen ions contributing to active acidity is, however, very small compared to exchange acidity. Now, it is estimated that exchange acidity may be 1,000 times greater in a sandy soil and 5,000 times to 100,000 times greater for a clayey soil high in organic matter. Now guys, again, this is soil fertility and plant nutrition. So if you have any questions, you can ask in our WhatsApp group or comments, or if you are not comfortable to ask in our WhatsApp group, then you can ask your question directly to me. So that's it for today, and enjoy your day. Thank you very much.